Swayam Prabha. Digital India. Educated India.
Just to show you another functionality that can be implemented using control sources, we consider how to scale the value of an element. Okay. And in this case, I will take a capacitor as an example, but you could equally well use some other element. So let's say I connect a voltage source V across the capacitor C, and this draws a current C times the time derivative of V. Okay. Now I have a variety of control sources, but for now let me consider a current controlled current source. Let's say this is Ix and this is some K times Ix. Okay. Now let's say that I want to alter the characteristics between these two terminals in some way. I want to scale it. What I can do is the following. I will sense the current flowing through the capacitor using the input branch of the current controlled current source. Now you observe that absolutely nothing has changed as far as the capacitor is concerned. The voltage across the capacitor is still V because this part is a short circuit. It's just a wire. Okay. So the voltage across the capacitor is still V. So the current through the capacitor is still C times dV by dt. Okay. Now if you look at the current through the current controlled current source, it is K times C times dV by dt. Okay. Now let me do one thing. Let me take the controlled current and also connect it across the voltage source which is driving the capacitor. Okay. Clearly you will see that the current that is drawn from the voltage source will be K plus 1 times C times the time derivative of V. We have C times dV by dt in this wire and K times C times dV by dt in that wire. So the total current drawn is K plus 1 C times the time derivative of V. Now again, let me enclose this entire circuit in a box. Okay. And look at only these two terminals. What do I have? It says that if I connect a voltage V to this whole box containing this, it draws a current K plus 1 times C times the time derivative of V. So it means that this entire box here looks like a capacitance of value K plus 1 times C. Okay. So what do I mean by it looks like that? If I gave you two boxes, one consisting of this capacitor C and a current controlled current source of value K connected up like this, and another box which has actually a capacitance of value K plus 1 times C, there is no way you can distinguish between the two. You cannot tell which is which by measuring voltages and currents at the two terminals. Okay. And that is what is in general meant by equivalent circuits. Okay. So you could have a box with very complicated circuitry here, but let's say across the terminals you measure the voltage and current and come up with a relationship V equals I times something. Now you know that that relationship belongs to a resistor. So this whole entire complicated circuit within the box cannot be distinguished from another box which consists of a single resistor of that value. Okay. So without opening the box you cannot tell what is inside. As far as the terminal characteristics are concerned, it is just a resistor. Similarly, in this particular case, as far as the terminal characteristics are concerned, it is just a capacitor. Okay. So now this kind of scaling of element can also be achieved using a voltage controlled voltage source. Okay, one example of that, which is quite popularly seen in circuits. I'll show that here without discussing it too much. So let's say we have a voltage controlled voltage source with a scaling factor K. Okay. Now, let me do a few things. Let me connect these two parts together and let me connect a resistance R between these two. Okay. Now, I'll enclose this whole thing within a box, and what I'm interested in is finding out the equivalent characteristic between these two terminals. Okay. What do I mean by finding the characteristic between these two terminals? As I mentioned before, you have a box with these two terminals, and what you have to do is to determine the current voltage relationship, where the current and voltage are measured at the two terminals. Okay. So that's what is meant by finding the equivalent behavior or finding the equivalent circuit and so on. Okay. And the way to do that is you either apply a voltage source V and determine the current I. Alternatively, you can also apply a current source I and determine V. Both these are possible. Some of them are more convenient in some contexts. Okay, but the two are perfectly equivalent. Once you do this, you know the relationship between V and I, and you will be able to tell what the equivalent circuit is. Now, for this particular case, let me apply a voltage V. Now, because this Vx equals V by Kirchhoff's voltage law, very simple application of it, the voltage across this is K times V. Okay. And again, by Kirchhoff's voltage law, the voltage across the resistor in this polarity is V minus K times V. Okay. So the current drawn from the source will be equal to the current flowing in the resistor, which is this voltage divided by the resistance value. So it is V times 1 minus K divided by R. Okay. And you know from Ohm's law that whatever is multiplying V is the conductance between these two terminals. Okay. So this between these terminals, it looks like a conductance of value 1 minus K by R, or a resistance of value R by 1 minus K. Okay. So you can, if you have a physical resistor R, by connecting it up with a voltage controlled voltage source like this, you can change its value. You can also see what happens with this. If K is smaller than 0, let me call this the effective resistance R effective. R effective will be smaller than R, and if K is between 0 and 1, Okay. R effective will be more than R, and if K is exactly equal to 1, R effective will be infinity. That means that it looks like an open circuit. Okay. What does it mean if K equals 1? This voltage is exactly the same as that voltage. There is no voltage across R at all. Although there is a resistance, it does not draw any current because the voltage across it is 0. And finally, if K is more than 1, then R effective will become negative. Okay. So you can take a resistor, make it look like it is smaller, make it look like it is larger, make it look like even an open circuit, or you can even make it look like a negative resistance. Okay. So these are all not for any specific purpose at this point, but to illustrate the possibilities. But later, when you go to active circuits, you see that some of these concepts are actually used in practical circuits. Okay. Sometimes you will need to change the values of resistors for various reasons, and these things are used. Okay. So that's in summary the utility of control sources. They are used for modeling and abstraction of complicated circuits into simple models, as well as for synthesis of exotic functions. Okay.